This is going to be a discussion about numerical and graphical approaches to limits. Now before you watch this is under the assumption that you have already covered the introduction to the tangent problem and the introduction to the velocity problem, because we will be referring to those in this lesson. So first, why do we talk about limits? Why do we care? Well, when you looked at the tangent problem and the velocity problem, believe it or not, they came up. It may not have been called a limit at the time, but it is what we were discussing. If you remember from the tangent problem, as the x-coordinate approached 1, the slope of the secant lines that we were looking at got very close to 2. We ended up looking at the slope of the secant lines to guess that the slope of the tangent line was going to be 2. Here's the numerical calculations that we took a look at. When we had an x-coordinate of 2, if you recall correctly, this was not an xy table. This was actually an xm table, m being the slope. So these were the slopes of the secant lines for these x-coordinates. So when x was 2, the slope of the secant line was 3. When x was 1.5, the slope of the secant line was 2.5, and that continued on. And it seemed like the closer we let x get to 1, the closer the slope got to 2. Well, that's actually a limit. When we talked about the velocity problem, as the time intervals got smaller, and that meant that the time was approaching an exact value of 5 seconds. We looked at the time interval from 5 seconds to 6 seconds, from 5 seconds to 5.5 seconds, etc. And as that time approached 5, the average velocity appeared to get close to 49 meters per second. That's also a limit. So when we talk about what is a limit, suppose f of x is defined when x is near the number a. So in other words, your function is defined for values of x close to some number a. There's 3 things you want to look at anytime you're introduced to new notation in math. You want to look at what we write, what we say, and what it actually means when we say it. So what we write for limits is this notation here. The limit, the f of x, and the equals and the L are all in one line. The x and the arrow and the a go directly under the limit sign. What we say as we write this, we say the limit of f of x as x approaches a equals L, or as x gets close to a, f of x gets close to L. Okay, so that's what we say when we write it. What that means, the mathematical definition is, we can make the values of f of x arbitrarily close to L, meaning as close as we like, by taking x to be sufficiently close to a. Okay, so let's translate that a little bit. In other words, x is getting close to a. A is typically a number. It is an x value because x has to be getting close to that x value. So as you let x get close to whatever x value a takes on, your function value, in other words, your f of x, meaning your y value, your y should be getting close to L, which means L is also a y value. So we can make f of x, your y value, close to this limit, L, by taking x sufficiently close to a. That's what we mean by a limit. But the important part to this, we're not done with the definition. The important part is right here. But not equal to a. Let me say that again. But not equal to a. Meaning, this is all about what happens when x is close to a. Not what happens when x is equal to a, but when x is close to a. And let me give you a graphical example to kind of illustrate what I'm talking about. If we look at a graphical limit, that literally means we're going to look at a graph to try and determine a limit. So we have an x-axis, a y-axis. X should be getting close to a. So here's my function. The blue curve is my function. So x values, they increase as you move right, decrease as you move left. So if x gets close to a, meaning it's approaching a, there we go. Notice your y value in this case is getting close to L. So as x approaches a, y approaches L, or f of x approaches L. Now let's take a look at this one. This one's a little bit different. They are remarkably similar, but this little spot right here is actually different. That's an open circle. That point does not exist on this graph. So the ordered pair a comma L, x coordinate of a, y coordinate of L, doesn't exist on this graph. This graph is undefined at a. But remember, the limit isn't about what happens at a, it's about what happens close to a. So when you look as x gets close to a, the y value, the function value, is still getting close to L. So in both of these cases, we say that the limit as x approaches a on f of x equals L. It's true in both cases, whether it's defined at a or not. Let me give you a third scenario. Again, very similar graph. This is still undefined at a on this part of the function, but if you notice there's this little dot right here. This actually is defined at a. This is an ordered pair that has an x coordinate of a, and I don't really know exactly what the y coordinate is because there's not a scale on this, but the y coordinate is whatever that y is right there. So when we look at this, if you plug a into this function, you don't get L. But limits aren't about what happens when you plug in a. They're not about what happens at a. They're about what happens near a. As x approaches a on this function, the function is still approaching L. This is still true in this case. So in all three cases, I'm going to write it again. The limit as x approaches a on f of x is absolutely equal to L. So let's take a look at an example on this graphical limit. So if we look at this example, if we talk about the limit as x approaches 2 on this graph, as your x values approach 2, your y values are approaching 3. So we say that the limit as x approaches 2 of f of x is equal to 3. Notice this function is not defined at 2, but the limit is still going to be equal to 3. If we take a look at a very similar graph, when I draw this one, the only difference is, well, it should be very close to the one to the left. It still has the open circle at 2, 3, but I've put in a closed circle at 2, 1. When we talk about the limit as x gets close to 2, not at 2, but close to 2, does this change our limit value? Well, if you look, when x gets close to 2, so here's x equal to 1, 1.5, 1.9, etc. As long as you're close to 2 and not at 2, this limit is still equal to 3. So the fact that we have a closed circle down here that has an ordered pair of 2, 1 does not change the limit because, again, it's about what happens near 2, not at 2. So that's graphical approaches to limits. Let's take a look at a numerical approach to a limit. We've actually already done some of this when we looked at the tangent and the velocity problems. Basically, numerical limits are found using numerical calculations of values of x getting increasingly closer to x. They're called numerical because you are plugging in a lot of numbers and doing a lot of arithmetic and a lot of calculations. We've looked at a couple, but let's take a look at a new one. Let's find the limit as x approaches 9 on the function x minus 9 divided by the square root of x minus 3 by evaluating the function at x equals 8.9, 8.99, 8.999, and x equals 9.1, 9.01, 9.001. Notice in both of these cases you're getting numbers that get very, very close to 9 without actually achieving 9. If we take a look, here is my calculations on those. Let me show you how I got one of them. So for example, when x was equal to, let's say, 8.9. The way that I did that, I just took 8.9 minus 9 and divided it by the square root of 8.9 minus 3. And when you put that into a calculator, what you get is 5.9833. That's of course only out to 4 decimal places. This goes on farther, but so that's how I'm getting all of these numbers. I'm letting the calculator do those for me. And if you notice, as we put in 8.9, 8.99, 8.999, watch what's happening to the y value, to the function value. I'm getting 5.98, 5.99, 5.999. It definitely appears like my function is approaching 6. Let's check the other side. If we look at 9.1, 9.01, 9.001, these also appear individually. You kind of got to look at these as two separate things. These appear to be approaching 6 as well. So what we will say is that the limit as x approaches 9 on x minus 9 divided by the square root of x minus 3 appears to be equal to 6. Now, you're hearing me say appears to be, and that's going to illustrate the drawback. Calculating limits using graphical and numerical approaches have their benefits, but their major drawback is they are guesses, they are estimates. They're usually educated guesses and educated estimates, but they can be misleading if you're not being careful. And we will actually illustrate some of the drawbacks to them as we look at a couple more examples. But let's finish up this one just a little bit. If we take a look at a graph of y equals x minus 9 divided by the square root of x minus 3, this is its graph. And if you notice, as x is approaching 9, it does in fact appear that your y value should be approaching 6. Your numerical and your graphical approaches to these limits should agree. Just because they're different approaches doesn't mean they should get you different answers. One of the things you want to keep an eye on is check out the domain of this function. If you notice, I've asked you to find the limit as x approach 9. If you try to plug 9 into this, you're going to have a problem. You're going to get a 0 in your denominator. And what that means is that on this graph, there should be a hole sitting here, but you can't see it. And that's one of the major drawbacks of using calculators to do these kinds of problems. You can't see the holes. The calculators can't do the calculations quite exact enough to give you all the details that you should be able to pick up if you take a look at the algebra. Let's take a look at some of the other places our calculators can really cause us problems. Okay. Watch what happens when we look at a different function. This is a new function. We're going to look at the limit as t approaches 0 of the square root of t squared plus 9 minus 3, that all divided by t squared. And notice 0, if you try to plug it in, it's going to give you a 0 in your denominator. We're going to take a look at this numerically and graphically. If we look at it numerically, take a look at my values. T should be approaching 0. So I'm choosing values of t, by the way. This is not an xy table. This is a ty table. So there's another drawback of technology. It doesn't change your letters for you. You have to do that. You have to understand to do that manually. As t approaches 0, so I've chosen 1, 0.5, 0.1, 0.05, 0.01. Those are numbers that approach 0. And if you take a look, the y values do appear to be approaching specifically about 1.16 repeating, which, by the way, is 1/6. So the value for these values of t, it appears that the limit is approaching 0.16 repeating, which is 1/6. Great. But watch what happens when I use even smaller values of t. So here's 0.01. This is your calculator. This is its scientific notation. It's 1 times 10 to the negative 4th. So 0.0001. That's what it's writing here. Add another 0 here, another couple of zeros here. Notice it stays at 0.16 repeating, 0.16 repeating, and then it kind of starts to have a little problem. And then all of a sudden, if you make that number, that x value, that t value, excuse me, if you make that t value close enough to 0, eventually it starts returning a y value of 0. Because of the limitations of your calculator, it's just not able to handle numbers this small. If you take a look at this graphically, it's actually going to do the same thing. If you take a look at this with using a window, this is a -5 to 5 on your x-axis. This is -0.1 to 0.3 on the y-axis. So these tick marks on the y-axis are a 0.1 scale. If you look in this scale, it agrees. This is 0.1, this is 0.2. So yeah, this seems reasonable to be about 0.16 repeating. Fantastic. But if I change the window, instead of going -5 to 5, I shrink that x window. The y values are staying the same. The y still goes from negative 0.1 to 0.3. If I make my x window go from negative 0.00001 to positive, same number, then what happens is instead of drawing the graph nice and continually this way, all of a sudden it drops it down to 0. And it's the same thing that happened with those numerical calculations. When you make these numbers close enough to 0, it can start to drop them and not be able to handle the calculations involved. Let's take a look at another way that our calculator can cause us some issues. So let's take a look at x approaching 0 on the sine of pi over x. I'm going to let x approach 0, and yes, we're going to put trig functions into these. So this is sine of pi divided by x. So all I did was pick x values that approach 0, so 1, 0.5, 0.1, 0.01, etc. And notice every single one of these is returning me a y value of 0, which means it would be reasonable based on this table to guess, hey, this limit must be equal to 0. But it's absolutely not equal to 0. Take a look at what happens when I use other x values, 0.22, 0.19, 0.03, 0.006. These numbers also approach 0. So this would count as taking a look at the limit as x approaches 0. But notice the y values. Not only are they not approaching one specific number, the first one's positive, the next two are negative, the one after that is positive. It's bouncing around between positive and negative numbers. Now, if you know what the graph of sine x looks like, that's not that big a surprise. But take a look at the graph of this one. This may be different than something you've seen before. Because of the fact that you've got an x in a denominator inside your sine function, you don't get the traditional oscillations of sine where they're nice and spaced out. What you get is something that starts off kind of slowly and then picks up its number of oscillations as it gets very, very close to 0. What this illustrates is that basically between here and here, and this is the origin right here in case you can't tell by the graph, you have infinitely many oscillations between before you can reach x equals 0. So this limit never actually approaches one specific value. So the moral of the story is calculators are very useful in calculus, but they have to be used appropriately. You should use them to do things like calculating the square root of 8.9. No one wants you to have to do that by hand. What you should not be using your calculators for is actually finding these limits graphically and numerically. Don't do that because your calculator can give you some very misleading advice. You have to understand the concept of what you're doing and use your calculator as a tool to make the arithmetic easier. That's what it's for. Let's take a look at an example. Let's take a look at this graph and answer the following questions. We're going to find the limit as x approaches negative 4 on this function. So x should be getting close to negative 4. So x value of negative 4 is over here. On your function, which is the red line up here, as x gets very, very close to negative 4, what is your function value approaching? Right, it's approaching 2. So the limit as x approaches negative 4 on this function should be 2. Let's take a look at the second one. Find the limit as x approaches 6 on this function. So as x is getting close to 6, here's your function. As x is getting very, very close to 6, remember this is close to 6, not at 6. So this little point down here isn't going to change my limit. As x gets close to 6, the function is approaching 5. Therefore, the limit as x approaches 6 on this function is 5. Let's take a look at the third one. Find the limit as x approaches 1 on f of x. So 1 is here. So if we start off on our function, we run into a little bit of an issue on this one. Because if you look at here, as x is getting close to 1, it appears my function is getting close to 4. But if you look here, as x is getting close to 1, it appears my function is instead getting close to negative 2. So it turns out we can't actually answer this question yet. We need to dig a little bit deeper into some other limit concepts before we can answer that. We'll come back to it though. We need to talk about one-sided limits. when we talk about one-sided limits, we say suppose f of x is defined when x is near the number a. So it starts off the exact same way. What we write is the limit. You've got, here's your x approaching a, f of x equals L. Most of that is the same. This is your new addition right here. The negative in the superscript. What we say when we write the negative up in the superscript of the a is that this is the limit of f of x as x approaches a from the left equals L, or as x gets close to a from numbers smaller than a. Remember, traditionally on a number line, as you approach a number from the left side, the numbers you're coming at it from are smaller. Or we can also just shortcut what we're saying and just call it a left-hand limit of f as x approaches a. What we mean by that is that we can make the values of f of x arbitrarily close to L, so far it's the same as the other definition, by taking x to be sufficiently close to a and less than a. There's your difference right there. If you match it up to the original definition of just a limit, that's the difference between the two. So if we have a left-hand limit, chances are we also have a right-hand limit. So again, what we're going to write, we're going to put a positive, a plus in the superscript this time. And what we say with that is that the limit of f of x as x approaches a from the right equals L, or as x gets close to a from numbers larger than a, because you're coming at it from the right-hand side. And when you come at something from the right-hand side, you're coming at it from numbers larger than itself. Or we can just say it's the right-hand limit of f as x approaches a. And it means we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a and greater than a. That's your difference. Okay. So you may have already deduced the following. If you want to talk about the limit as x approaches a on f of x, notice the lack of the positive or negative in the superscript. That means this is an overall limit. Okay, that's if it's not a left and it's not a right, we tend to call it an overall limit. So this overall limit is equal to L if and only if the limit as x approaches a from the left on the function is equal to the limit as x approaches a from the right on the function and is equal to L. Now, be a little careful. That's a number. L is a finite value. We'll talk about what happens if it's not later. So in other words, the only way to have an overall limit equal to a number is if the left-hand limit and the right-hand limit agree on that number. So take a look back at this graph and go with these questions this time. We've already talked about it's the same one we dealt with before. We already talked about the limit as x approached -4 on the function and the limit as x approached 6 on the function. So now let's talk about this one. Find the limit as x approaches 1 from the left on this function. That means x should be approaching 1 from numbers smaller than 1, physically on the left side of it. So 0.9, 0.99, etc. If you were thinking of this numerically instead of graphically. That's up here on your function. You're coming at 1 from numbers smaller than 1. So from the left side, this limit is equal to 4. If we take a look at the limit as x approaches 1 from the right on f of x, you should be approaching 1 from numbers larger than 1. So 1.1, 1.01, 1.001. So over here, as you approach on your function x values close to 1 but larger than 1, your y values are approaching -2. So when we ask what is the limit as x approaches 1 on f of x, this was the question we couldn't answer before. Notice the left-hand limit is 4, the right-hand limit is -2. Your left and your right do not agree, which means overall this limit does not exist. And that is abbreviated, of course, shorthanded, DNE. It doesn't exist because the left and the right don't agree. So let's talk about what happens when that limit value is not a finite value. Okay? Some functions tend to get infinitely large or infinitely negatively large as x approaches a. When we say negatively large, we mean -1 million, -1 billion, etc. So if that happens, technically these limits do not exist, because by definition of a limit, we would need to be able to get arbitrarily close to infinity or negative infinity. Well, infinity is a concept, it's not a number, so you can't get close to infinity, because no matter how close you get, you can get infinitely closer. So technically these limits don't exist. We call these infinite limits, but we do try to answer them whenever possible as the limit equaling infinity or negative infinity. They're equal, but we'll talk about what that means, because it doesn't mean the same thing as when it equals a finite number. So let's take a look at what we mean by an infinite limit. So again, suppose f of x is defined on both sides of a, except possibly at a itself, because for limits, you don't need to be defined at the number. What we write is that the limit as x approaches a on f of x equals infinity. What we say, the limit of f of x as x approaches a is infinity, or as x gets close to a, f of x increases without bound. That's what that means. Mathematically, it means we can make the values of f of x arbitrarily large by taking x to be sufficiently close to a, but not equal to a. We can also say that if we have the limit as x approaches a on f of x equals negative infinity, or as x gets close to a, f of x decreases without bound. Okay? And that would just mathematically mean we can make the values of f of x arbitrarily large negatively by taking x to be sufficiently close to a, but not equal to a. This is a little cumbersome to say arbitrarily large negatively, but we want to avoid using the word small, because when we say small, we do not mean negative a million and negative a billion. What we mean is 0.0001. So we do need to refer to that as arbitrarily large negatively. So let's take a look at the limit as x approaches 0 on 1 over x squared. Now we can do this numerically or graphically. Those are the two approaches we have discussed thus far. If we evaluate it numerically, we evaluate at x values getting close to 0. But now that we've talked about left and right hand limits, you need to make sure that the left and right hand limits agree. So for example, if you're coming at 0 from 0.5, 0.1, 0.01, 0.001, are you coming at it from the left, or are you coming at it from the right? You should be coming at it from the right, because those are all numbers larger than 0. Whereas when we come at it from negative 0.1, negative 0.01, negative 0.001, those are all numbers smaller than 0. So these are your left-hand limit. Notice as you approach 0 from the right, that's up here, you go from your y values, your function values, go from 4 to 100 to 10,000 to 1 times 10 to the 6th power, which is a large number. So notice they're getting infinitely large. So on the right side, it seems to be approaching infinity. Check the left side. It goes from 100 to 10,000 to, again, 1 times 10 to the 6th power. So again, very, very large. So since the limit as you approach 0 from the right side on 1 over x squared equals infinity, and the limit as x approaches 0 from the left side on 1 over x squared also equals infinity, the overall limit, which is just the limit as x approaches 0 of 1 over x squared, seems to be approaching infinity. So, but you can also do this graphically. The graphical approach is to look at the basic shape function. And what I mean by that, whenever you see basic shape, that means we expect you to be able to graph this without the use of your graphing calculator. So again, make sure you're using your technology appropriately. 1 over x squared is your smokestack graph. It should have a vertical asymptote at 0 and a horizontal asymptote at 0. Here's a picture of the graph right here. If you take a look as this approaches 0 from the right side, notice it goes up to infinity. And as we approach 0 from the left side, it also goes up to infinity. So in both cases, this limit should be equal to infinity. Let's instead take a look at the limit as x approaches 2 on 1 over x minus 2. And again, we can do this numerically or graphically. If we look at it numerically, we evaluated x values getting close to 2. Make sure to check that the limit is the same from both the left and the right. So again, if I'm getting close to 2, here are 2 different calculations. Here's 1.8, 1.9, 1.99, etc. So are these approaching 2 from the left or approaching 2 from the right? These are approaching 2 from the left because they're all smaller than 2. These are all approaching 2 from the right because they're larger than 2. Now this time notice though that as you approach 2 from the left, these numbers are getting negatively large, whereas when you approach it from the right, these numbers are getting positively large. So notice the limit as x approaches 2 from the left on 1 over x minus 2 equals negative infinity, and the limit as x approaches 2 from the right on 1 over x minus 2 equals positive infinity. Since your left limit and your right limit do not exist, that means that the limit as x approaches 2 on 1 over x minus 2 does not exist. Technically, when they equal infinity and negative infinity, they don't exist anyway because they're infinite limits. But when they get disagreement on the left and the right, they a little extra don't exist. You can also pick this up graphically. Again, this is also a basic shape graph. This is a graph of 1 over x, which is your reciprocal graph. And you have a minus 2 attached to your x. So whenever you add and subtract numbers from x, it's either a left shift or a right shift. Because this is a subtraction of 2, that shifts 1 over x to the right. So 1 over x, shift to right. Okay, there's a vertical asymptote sitting here. And notice as you approach from the right side, you get positive infinity. And as you approach from the left side, you get negative infinity. So again, your numerical and your graphical should agree. They are both guesses, but they should agree with each other. So here's the conceptual warning, that when you talk about an infinite limit, it's not a true limit. Technically, because they do not equal a finite value, meaning an actual number, these limits do not exist. So when we say that they are equal to infinity, what we actually mean is that they increase or decrease without bound, depending on whether you're talking about positive infinity or negative infinity. So be a little careful with that. One last thing to talk about with infinite limits. If you notice, these happen to occur around vertical asymptotes. If you recall from pre-calculus, when we give you a function, something like, f of x equals 1 over x plus 5, we expect you to be able to find the vertical asymptote of this by setting the denominator equal to 0. So we expect you to know how to find it, but we never actually defined what a vertical asymptote is. You know they can't be crossed. You know how to find them, but what is a vertical asymptote? Well, the reason we never defined it for you is because it requires a limit definition to talk about it. So the line x equals a is called a vertical asymptote. Here's your definition of the curve y equals f of x if at least one of the following is true. So either the limit as x approaches a on f of x equals infinity, as you approach a from the left, f of x equals infinity. As you approach a from the right, f of x equals infinity. And then the same 3, but with negative infinity. Either the overall limit is equal to negative infinity, the left-hand limit is equal to negative infinity, or the right-hand limit is equal to negative infinity. If any one of these 6 conditions is met, then what you have is a vertical asymptote. Okay, so we just looked at an example where this happened, but traditionally, when you look at these, we've got a vertical asymptote, and a few things can occur. You can get the smokestack that we just talked about, in which case your overall limit equals infinity. You can get where you get going to negative infinity on one side and positive infinity on the other side. We just talked about one of those. So, but both of these examples meet 2 conditions, not 1. What's going to pop up a little bit for us here, that's the more common thing to happen with the vertical asymptote, but every once in a while you get this kind of behavior. So this is my vertical asymptote here, and I'll start off with this, but then you'll get a graph that does this. and that's an open circle right there. Now notice, as you approach this from the right side, this does not go to positive or negative infinity. Now that's an open circle, so it doesn't exist at the vertical asymptote. That's usual. You can't cross a vertical asymptote. Nothing has changed. But it doesn't have to approach positive or negative infinity on both sides. This is still a vertical asymptote because of the fact that if you come at this a value, whatever that is, from the left side, the function value decreases without bound or approaches negative infinity. It only has to happen once for it to be a vertical asymptote. Let me get you a prettier picture of that. Here's what it looks like sometimes. So here's one where as you approach from the right, it goes down to negative infinity. As it comes in from the left, that's going to be an open circle. But again, be careful about using graphing utilities for this because it may not be obvious that that's an open circle.